Hello, cutie patootie, math angel. Welcome back. This is Decaf-Math ASMR. Thank you for tuning in today. I hope that you're doing well. I'm excited for today's video because I will be looking to prove this statement right here. As you can see, there are absolutely no numbers involved at the moment. We have a little zero right here, but I promise that this is absolutely a mathematical proof. So, this is interesting to me anyway, and I hope that you like it. But even if you want to just sit back, relax, zone out, or even fall asleep, that is perfectly okay too. For context, this is a very basic concept from a real analysis class, and I think a lot of math majors in uni or college or whatever that is for you would consider this to be a first quote-unquote real math major class. No pun intended, real as in the real numbers, but a real math major class as in pure math. And so I think if you go into college or uni knowing that you want to be a math major, most likely you have enjoyed math in your classes so far, and I think most math majors would have taken calculus at the latest in high school. Not that that has to be the case, but I mean for most people who know ahead of time instead of realizing that that's something that they might want to go into. Most likely you would have taken calculus before college, and because of that, this is kind of a first class where you revisit those ideas. Real analysis is basically calculus plus plus, where you revisit concepts but in a much more elegant and abstract way. So I just thought that this would be really cool to look at in this new framework here. So there's no brush or anything. Of course, it's still Decaf-Math. I don't really care what your relationship with math is. If you like it, hate it. I don't even care if I know this or not. I don't have anything to prove or show or anything. So it's just us hanging out, enjoying, being curious, and I'm just really excited. So I also kind of feel like this is an in-between topic because I feel like either you've learned calculus and this is still new to you, so this might be really interesting to think about things in this new epsilon way. We'll talk about that, but in this new epsilon way. And I've made a video on epsilon delta definitions of limits, so it's kind of similar to that here. But I also kind of have a feeling that if you don't care at all, this might just be really abstract and just something nice to zone out to. Or on the other end of that, if you've taken real analysis, you're the kind of person who's just really fluent with concepts from topology, abstract math in general. This is going to be very, very basic for you. So whatever the case, we're all loved and welcome here. So I just thought I would give you context because I actually don't know where a lot of people are on their math journey, and if they're learning it, I kind of like to check in, but I don't really know. So there we go. So we're just gonna keep playing around, okay? So let's read this out loud first. I'm going to do this in Sharpie, which is actually pretty bold of me to do, but b in R, the set of real numbers. So in other words, if we have two real numbers, A equals B if and only if for all epsilon greater than 0. The absolute value of A minus B is less than epsilon, epsilon, epsilon. Okay, so actually, conceptually here, you don't really need calculus at all. Here, as long as you understand that A equals B, so what that means for two numbers to be equal. And the idea of absolute value here, I think you'll get the gist of what we're talking about. So, A equals B, this is actually kind of like a definition, if anything else. So, we have two real numbers, they are going to be equal if and only if, which means that we need to do a two-way proof. So we need to show that if this is true, if A equals B, then da 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 da. And then we also need to show if da 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 is true, then A equals B. So for this part, I think this is the first thing to kind of start getting used to for analysis, is this idea of instead of really, really close to, like we say in calculus, like a limit or something approaches something, it gets really, really close to that. This is a more precise way of thinking. So we're saying for all epsilon greater than 0. So if I pick any number greater than 0, we'll call that epsilon. Then this absolute value of A minus B, which is the distance between the two numbers, is less than epsilon. Now where this actually gets interesting is when we consider very, very small numbers, small epsilon values. And so then this absolute value is the absolute value that we might be familiar with from algebra or pre-calc or wherever you learned about absolute value. I'll have to look back if I've made a video on absolute value or not before, but if not, I can definitely do so. But this is the positive distance between the two numbers. And so if you think about small epsilon values, if you say 0.002, let's say, if you're saying for all really small epsilon greater than 0, if the distance between them is still less than epsilon, then they are basically equal. So if I have 0.00004 and I say that the distance, the positive distance between them is less than 0.00004, but then I find another really, really, really small number, because this is for all epsilon. So for any number greater than 0, the distance is less than epsilon. So basically, that means that A has to equal B. So, epsilon, like I said, can be any number greater than 0, but where this actually, like the power of this statement actually relies on epsilon being very, very small. And that's what we mean by approaching or getting really, really close, infinitely close. So, now let's begin our actual proof here. So we want to show if A equals B, then for all epsilon greater than 0, this is true. So we're going to go both directions. So this might be helpful to review different types of proofs or different strategies that we need to take. So for if and only if, we have to do if this is true, then this is true, and if this is true, then this is true. So first, let's assume that A equals B, so it's given. And I don't have this kind of sketched out exactly, so forgive me if it's not perfectly phrased, but hopefully I can highlight the logic here. So if A equals B, 0, the absolute value of a minus b is less than epsilon. So then the absolute value of a minus b, so the positive distance between the two, is going to be 0. And that's because a equals b. You can do a little substitution here if you want. You can do, since a equals b, they are the same. So a minus, you might as well substitute b with a, or you can do b minus b. Either way, you get the absolute value of 0, which is 0, right? And for a little review here, this is the absolute value. So if the difference between them is 5, for instance, the absolute value of 5 is 5, and the absolute value of negative 5 is also positive 5. You're just taking the positive part. Again, conceptually, we can go back through that, but the absolute value of 0, so the distance from 0 to 0 is 0. So we have that the absolute value of a minus b is equal to 0, but epsilon is greater than 0. If we chose an epsilon that is greater than 0, then this is equal to 0, which will be less than epsilon, because for all epsilon greater than 0, because literally epsilon is greater than 0, so it's kind of just by default. Does that make sense? I know it might seem really simplistic and obvious, but figuring out in which direction and how to actually write this out is pretty much half the proof. Same thing for epsilon delta proofs, is to figure out what we're letting things be. So in this case, we just showed that given a equals b, then the absolute value of a minus b is 0, which for all epsilon greater than 0 is going to be less than epsilon. So given this, this is true. So now let's go the other way. So going the other way, we want to show, given that if for all epsilon greater than 0, and that the absolute value of a minus b is less than epsilon, so that would be given, then we want to show that a equals b. So this is going to be kind of harder to show in general, just going if and then this, but we can assume we can do this by contradiction. So let's see, so if we can do assume for the sake of contradiction, which you want to say, because you can't just assume, like you're saying you want to show that a equals b, so if you're saying assume for the sake of contradiction that a doesn't equal b. So this is a proof technique, which is if we're saying if this, then you're saying if for the sake of contradiction I assume that this is not true, so I'm going to assume that a is not equal b, then I want to somehow logically trace back to a contradiction to our original given, so that we could say that this is, the assumption is wrong. There is a contradiction somewhere. If we have this contradiction, then that means that our original assumption was wrong. So we are going to assume that a doesn't equal b, and hopefully we then get some kind of contradiction within this somehow. So what we're going to do here is say if a does not equal b, so since now we're given, or we're assuming that a is not equal to b, then the absolute value of a minus b is going to be greater than 0. Because as we showed here, if a equals b, it's going to equal 0, and the absolute value function, so I'll just kind of note this here. The absolute value function is either 0 or greater than 0. In other words, greater than or equal to 0. But I'm writing it like this because I want to emphasize the fact that if a equals b, then this would equal 0, but since it does not equal b, then it's definitely greater than 0. Does that make sense? So I kind of just crossed out this situation for that reason. Okay, so that means that definitively the absolute value of a minus b is greater than 0, which now we want some kind of contradiction here. So if I can show that there is some epsilon, if there's some epsilon greater than 0, where this would not be true, then we have some kind of contradiction. So if I let epsilon equal this, if I just let epsilon straight equal this absolute value of a minus b, just by choice, right? Because this should be true for all epsilon greater than 0. So if I can find a particular case where that's not true, then that's going to be my issue there. So if I let epsilon equal to absolute value of a minus b, and this epsilon is greater than 0, then we have absolute value of a minus b is less than epsilon, because that's given here, but this epsilon is greater than 0, which is equal to a minus b. And you don't necessarily want to write, inequalities and equations like this, but logically you're basically saying that the absolute value of a minus b is less than the absolute value of a minus b. And that's our contradiction, because a number, whatever this absolute value is not going to be less than itself. Like 5 is not less than 5. It's equal, right? So, again, logically it seems kind of silly to write out, but the trick is to pick the epsilon that gives you the contradiction, right? So, if I realize that I got a little cut off here on the paper, so let me just retrace a little bit. So basically, if I let epsilon equal the absolute value of a minus b, but based on this given part, the absolute value of a minus b is less than epsilon, but epsilon is equal to the absolute value of a minus b, because this should work for all epsilon, so it has to work for the one that I choose. But in this case, it doesn't work because this number, a number is not less than itself, so that's my contradiction. So therefore, my assumption was wrong. And therefore a must equal b. And that's it. So if for all epsilons greater than 0, the absolute value of a minus b is less than epsilon, then a must equal b. And we just showed this proof in both directions. Okay, and so like I said, this is actually more of a definition type proof. It kind of gives you more intuition of what a equals b and what it means for two real numbers to be equal. And this distance, this absolute value of a minus b, is how we mathematically show or define on this metric the idea of distance between them. The difference, but it's the positive difference between them. So for all epsilon greater than 0, and most interestingly, very small numbers, epsilon, if for all really small numbers greater than 0, if that distance is less than epsilon, then they are equal to each other. I hope that this was interesting to you, if this is new. And if you are asleep right now, I'm wishing you sweet mathy dreams. If you're going to continue on with the rest of your day, I hope it's a good one. And we'll keep jumping around with math and ASMR and math here. Just having that you'll subscribe if you enjoyed this video and haven't already.